there, Mrs. Saunders here. Welcome back to the epic saga of calculus, where we're not just solving problems, we're telling a story. In the late 1600s, Europe stood at the brink of a scientific revolution. Astronomy was becoming measurable, physics was turning from philosophy into a predictive science, and the boundaries of mathematics were ready to be pushed. But to do that, something essential was still missing. A way to measure change precisely. A way to calculate motion. Not just between intervals, but at exact moments. The groundwork had been laid. Descartes had given algebra a home on the coordinate plane. Fermat had experimented with tangents, but a new kind of mathematics was still waiting to be born. And this is where our story picks up. In the quiet countryside of 17th century Lincolnshire, England, a solitary, intense young man named Isaac Newton joins our story. Newton was born prematurely on Christmas Day in 1642, and then was raised mostly by his grandparents after the death of his father. His mother remarried when he was just 3 years old, leaving young Isaac behind in the care of his grandmother, a wound that would shape his deeply introspective and often mistrustful personality. Newton did not thrive in his early schooling. He was more interested in building mechanical toys and sundials than windmills than mastering Latin or rhetoric. Yet a turning point came when a former teacher recognized his raw intelligence and convinced his family to send him to Cambridge University. At Cambridge, Newton absorbed every idea he could find, not only the classic curriculum, but also the emerging works of Kepler, Galileo, Descartes, and Wallace. He copied entire texts by hand into his personal notebooks, working through their logic obsessively. He rarely participated in class, but his understanding deepened in silence. But then came the plague of 1665, which forced Cambridge to shut down and sent Newton home once again. This period of isolation would become a breeding ground of innovation. In just 18 months, Newton developed the foundations of calculus, his theory of universal gravitation, and new insights into optics, a period he would later refer to as his most productive. Newton was driven by fundamental problems that had stumped mathematicians for centuries. How do you find the area under a curve? How do you determine the precise slope of a constantly changing line? And how do you describe planetary motion that speeds up and slows down? Newton was developing new mathematics to describe moving objects and changing quantities. Recall from episode 1 how Eudoxus used his method of exhaustion. He calculated the area of a circle by inscribing polygons with more and more sides, making the difference between the known polygon area and the unknown circle area smaller and smaller until it essentially disappeared. This was approximation with mathematical rigor. Newton applied this same logic to time and motion. Instead of using geometric shapes to approach a curved area, he used tiny slices of time to approach the true nature of motion, allowing him to analyze exactly what was happening at each instant. His fluxions are what we now call derivatives. They captured instantaneous rate of change. If a ball is thrown into the air, Newton's method could determine its exact velocity at any precise moment. These fluxions would become one of the twin pillars of what we now call calculus. Meanwhile, across the channel in Leipzig, Germany, another brilliant mind was pursuing similar questions. Gottfried Wilhelm Leibniz was born in 1646 into an intellectual Lutheran family. His father, Friedrich, was a jurist and a professor of moral philosophy at the University of Leipzig, and his mother, Katharina, she was the daughter of a professor of law. When his father died in 1652, 6-year-old Leibniz inherited something precious: access to an impressive library that would shape his voracious intellectual appetite. As a child, he was largely self-taught in the library of his father, which explains his early fascination with philosophy and theology and languages. At, get this, just 14, remarkably young even for that time, Leibniz entered the University of Leipzig in 1661, where he studied philosophy and mathematics, graduating with a bachelor's degree in 1663 at the age of 16. He earned his master's degree in philosophy at the age of 18 in 1664 for a dissertation relating philosophy and law to various ideas in mathematics. While Newton was isolated at home crafting his Fluxions, Leibniz was experiencing his own mathematical awakening in Paris from 1672 to 1676. He studied under Christian Huygens, the Dutch physicist who presided over the French Academy of Sciences, and became his mathematical mentor. Even more remarkably, Leibniz was able to access the unpublished manuscripts of Descartes and Pascal, cutting-edge mathematical work unavailable to the public. He began working on calculus in 1674, the earliest evidence of which is in his surviving notebooks of 1675. Leibniz focused on the tangent line problem. Like Newton, Leibniz was applying the method of exhaustion concept. He defined the tangent line through a pair of infinitely close points on a curve. He imagined the points on a curve getting closer and closer together until the secant line between them became the tangent line, the instantaneous rate of change at that point. But Leibniz's true breakthrough was creating a revolutionary notation system. Leibniz introduced his notation in 1675, which denotes a derivative as the quotient of two differentials. Well, what does that mean? His symbols were dx for a really, really small change in x, dy for the corresponding really, really small change in y, and dy dx, that was their ratio. And these symbols, they weren't just shorthand. They embodied the mathematical relationships themselves and could actually be manipulated like fractions. Where Newton's dot notation, which I'll show you later, was tied to time and motion, Leibniz's differential notation was universal. It worked for any function, regardless of what the variables represented. This systematic approach to notation would make calculus accessible to mathematicians across Europe, turning what had been Newton's private mathematical language into a tool that anyone could learn and use. So both men had arrived, independently, at a powerful new idea, the derivative. For the first time, mathematicians had a method to compute instantaneous rates of change, not just between 2 points, but at a point. Their approaches, however, revealed fundamental differences in vision. Newton viewed derivatives as instantaneous motion, change per moment. His dot notation emphasized rate over time, reflecting his concerns with how things move, like falling apples, orbiting planets, curving projectiles. He called his changing quantities fluents and their rates of change fluxions, grounding everything in a physical reality. Leibniz, in contrast, approached derivatives through symbolic abstraction. He saw derivatives as ratios of changes between variables represented by dy dx. He wasn't thinking only in terms of physical motion, but rather in terms of relationships between mathematical quantities. In essence, Newton's approach was grounded in the physical reality, while Leibniz's approach, it was more formal. Both interpretations, they were both correct, and they led to the same answers, but they reflected deep philosophical differences about what mathematics should even be. Now, as their ideas became known across the world, so did the similarities between their ideas, and the controversy began. Who invented calculus? Newton's followers, they accused Leibniz of plagiarism, claiming that he had had access to Newton's unpublished manuscripts. For Leibniz, these accusations were deeply unfair. He had published first, he had developed a genuinely different approach, and he had created superior notation, yet he found himself powerless against that English mathematical establishment. So, in desperation, he published an anonymous defense of himself, the Chart of Valence, but it fooled no one. Meanwhile, the Royal Society, with Isaac Newton as its president, launched an investigation and, predictably, ruled in Newton's favor, with Newton himself secretly writing the report. Newton's victory, it came at a terrible cost to both men and to mathematics itself. Leibniz died in 1716, branded as a plagiarist and largely friendless, never knowing that history would vindicate him. The controversies stalled English mathematics for decades, as British mathematicians remained loyal to Newton's fluxions, while continental Europeans embraced Leibniz's elegant symbols and superior methods. And the tragic irony? Well, modern consensus shows that both men independently developed their ideas, making the entire bitter feud unnecessary. Today, we use Leibniz's notation, but we honor Newton's physical insights. A synthesis that might have happened decades earlier if ego and nationalism hadn't intervened, but the damage was already done. What followed would be one of the most consequential battles in mathematical history, not over ideas, but over symbols. You see, it wasn't enough for Newton and Leibniz to invent calculus. Someone had to decide how the world would write it, teach it, and think about it. The notation war that erupted would determine whether mathematics advanced or stagnated, whether the nations collaborated or isolated themselves, and whether the language of calculus would help or hinder future discoveries. Next time, we'll witness the Great Notation Wars, where mathematical symbols became weapons, national pride trumped mathematical progress, and a single choice between dots and dy dx would shape the future of calculus for centuries to come. Thanks for being here. I'll see you next time.